Okay, so let us resume our discussion on the restoring method of division. So here we are trying to solve one example. We have two operands. We want to divide plus 136 by minus 8. Our operands are in signed magnitude binary. That means the sign bits are stored separately in flip-flops. And we are taking n bit registers to store the operand values. So clearly, as you can see here, our divisor is of size 4 bits. 9 is 1001 in binary, so that is stored in register B. The sign associated with the divisor is 1 because the number is negative, so we have kept this sign bit in BS. So basically here in this configuration, every register has its associated sign flip-flop. 136, if we represent this number in binary, it is 1000 without the sign. So 8 bits are needed to represent the magnitude. Now, as we are using 4-bit registers, we have to use two registers if we want to store this dividend fully. So we have taken two registers A and Q to store this binary number. And as this dividend, the first operand is positive, the associated sign is 0, and it is kept in two flip-flops, actually AS and QS. So here in this configuration, every register has its own associated sign flip-flop. So AS is the sign flip-flop related to A, and register Q has its own sign flip-flop QS. As A and Q represent the same thing, the same operand, the dividend, we have to store the actual sign, that is 0, because the number is positive in both AS and QS. So this is how the number is stored. Then we have also checked for the two possible errors: divide overflow and division by 0. So according to the logic of the restoring method, if we can comment on the relation, the magnitudes of A and B, then we can say whether divide overflow will occur. So here, if A is greater than B, then there are chances that a divide overflow will occur when you perform all the steps of the division according to the given algorithm. So in that case, the system cannot proceed further because the quotient will have n plus 1 bits in the last step, and you do not have that much space available in n bit register to store all n plus 1 bits. So that will create an issue, and that's why if A is greater than or equal to B, you cannot simply proceed with the restoring method of division. You have to stop. So to indicate this kind of error, restoring method of division uses one special flip-flop called DVF, divide overflow flip-flop. And if A is found to be greater than or equal to B, DVF is set to 1. So if DVF is set to 1, this is an indication for the computer to stop. It will not proceed further. It will The given operation will simply end. So that will happen if divide overflow is present, and this condition checking will actually take care of the second problem also, that is division by 0. So if you check for this condition whether A is greater than or equal to B, then actually two possible errors are being taken care of, that is divide overflow and division by 0. You don't have to perform any explicit steps to check for divide by 0. Okay, so here, if we consider our operands, A is 1000 and B is 1001. So clearly we can see that A is less than B, so no divide overflow will occur. But still, let us see what is the standard method to check whether A is greater than or equal to B. So we can perform subtraction on A and B, and based on the result of subtraction, we can say whether A is less than B or A is greater than B, or both A and B are equal. So here what we have done, A to do A minus B, we have taken 2's complement of B and added it to the first operand A. So we have basically performed this operation. A plus B bar plus 1, that is A minus B RHS, and the result of this subtraction goes to E and A. It is possible to have one additional bit after this subtraction, so that bit value will be kept in a flip-flop and carry flip-flop E. So E and A together will have the final answer of the subtraction. So here E is very important to decide the magnitude, the relation between the magnitude of A and B. So if E is 0, A is clearly less than b, in that case you have to simply set dvf to 0. But if e is 1, in that case a is either greater than b or a and b are equal. In either of these cases you cannot proceed. So if this condition is true, if e is 1, dvf is required to be set to 1 to indicate an error and instruct the computer to stop. So in this case, nothing else will happen if DVF is set to 1 and no actual division will take place. You have to proceed with the actual steps of the restoring method of the division only if DVF is 0. So this is very important. For any example, you have to first check whether DVF is 0. Okay, now to perform subtraction, you have actually updated A. You have stored the result of subtraction in A. But ideally, if you want to perform the given division operation, then A should have the original value back. So basically, you need to restore A once you decide for the divide overflow. So here you have used subtraction to update A. If you want to nullify this impact of subtraction, you can perform addition. So for that, uh, in either of the cases, whether e is 0 or e is 1, you should restore the original value of a back. So a plus b to ea, this operation should be performed even when e is 1. So if e is 0, then also you have to perform this addition. If e is 1, then also you have to perform this addition, so that uh, a will have its original value back. So this is the condition that you need to check for deciding whether there will be an error. Now let us start with the actual steps of the algorithm. So it is better to give the tracing of this algorithm, restoring method of division, in a tabular format to have more clarity. So in the first column we can write the operations that we want to perform in every iteration. In the second column, we will write the value of E, then the value of A, that is the high part of the dividend, and Q, that is the second part of the dividend. So A and Q together will define the dividend. And as this process is required to be repeated for a fixed number of times, we have to control the number of iterations by setting one sequence counter SC. So let us first write the initial configuration. So initially, E does not have anything. Do not initialize E with any value. A is the high part of your uh, dividend. So our dividend is actually AQ is actually 1000100 without the sign. We are not taking the sign bits into consideration in this table. We'll use them in the end to determine the sign of the final answer. So A will be 10000 and Q will be the low part, that is again 10000. Now should be initialized with the uh, total number of bits we have in the registers. So here is A, Q, and B. B is actually 9 without the sign. So this is our divisor B. So all these three registers are of size 4 bits. We have to initialize SC as 4, the first value, the initial value of the sequence counter. Okay. Now let us also include the steps of checking for overflow step in this table. So what we have to do, we have to perform subtraction on A and B. So we have to basically add 2's complement of B to A. 2's complement of B, that is B bar plus 1, is 0 1 1 1. Let us add it to A. No AND carry is generated. So E is clearly set to 0. Okay. Now as E is 0, DVF is set to 0, and you have to restore A by performing addition. So this is currently the value of A. We will add the actual B to it to have its original value back. And E is 1 because of this addition. Now the actual logic of the algorithm starts. So the first step of the division method, restoring method of division, is SHLEAQ. You have to consider E, A, and Q as a single entity. You have to consider them together, and you have to perform logical shift left operation on them. SHL stands for logical left shift operation. Okay, so all the bits are required to be shifted towards the left. So this one will obviously be discarded. This one will be shifted here. Then this three zeros. This one will be shifted here. The rest of the bits of Q, and as this is a logical shift, as a serial input, 0 will be inserted. Note that the first bit of Q is actually Qn. We are calling it Qn. Okay. Now after this shift, you have to inspect what value is available in E. So as E is 1, you have to perform this subtraction. A minus B to A. If E is 0, then also you have to perform subtraction, but that would be A minus B to EA. Here we are not required to maintain the additional bit if it gets generated through subtraction. So A minus B is implemented as A plus B bar plus 1. So we can directly add B bar plus 1 to A. So we have already found B bar plus 1 here. So 0 triple 1 can be added to this. No AND carry is generated. So obviously the value of E will not be updated. And anyway, we have decided to keep the result of subtraction in A. So it will not affect E. Now, after this subtraction, you have to set Qn to 1. That means, what does this signify? Qn is set to 1 to indicate that one subtraction is already done and we have found the first bit of our quotient. In the end, you will get the quotient value in register Q and remainder in register A. So we are setting Qn as 1 to indicate that one bit of the quotient is found through the subtraction. Rest of the bits of Q will not be affected, they will remain the same. And this is the end of the first iteration. So you have to decrement SC by 1. SC is still not 0, so you have to continue this process. Okay, so let us start with the next iteration. This is the first iteration. Second iteration, again you have to start with SHLEAQ. So this one will be discarded. All the bits will be shifted towards the left. And here 0 will be inserted as the serial input. Now again the value of E is 1. So as E is 1, you have to perform subtraction, but you will not maintain the AND carry if it gets generated. So you have to add 0 triple 1, that is B bar plus 1 to A, to get the result of the subtraction. So this will be 0 triple 1. E will not be affected, and you will set Qn to 1 because now you have found the second bit of the quotient. Note that the rest of the bits of the Q will not be affected, they will remain the same. So this is the end of the current iteration. So you have to decrement SC by 1. SC is still not 0, so we'll continue with the process. Again, you have to shift EAQ towards the left. So 0 triple 1 0 0 double 1 and 0 is inserted as the serial input. Now E is 0. So if E is 0, you have to perform subtraction, but that result will go to E and A. So let us add B bar plus 1 to A to perform subtraction. Okay, after this subtraction, E is updated. One AND carry is generated, that is obviously a 1. So as now E is 1, that means the subtraction you have performed is correctly done. After this kind of subtraction, if E remains a 0, that means subtraction cannot be performed, but as you have already performed it, you have to nullify that effect of subtraction by performing addition. So basically you have to restore A in the case where subtraction is not actually possible, but you have already performed it. So here that is not the case. E has become a 1. So what you can do, you can simply set Qn to 1, rest of the bits of the Q unchanged, and mark this as the end of the iteration. So here Qn is set to 1, here also Qn is set to 1. SC is still not 0, so one more iteration is to be performed. So again, start the new iteration with SHL EAQ, and here 0 will be inserted. Now E is 0, so you have to perform subtraction but keep the result in E and A both. So we are adding B bar plus 1 again to do A minus B. AND carry is generated and that is 1. So it is possible to have this subtraction. The subtraction is done correctly. So you have to simply set Qn to 1 and rest of the bits of Q unchanged. Decrement SC by 1, so now it becomes a 0. That means this is the end of the operation. Now where is the final result? So Q and A, these two registers are important to show the result, the final result of the subtraction. So Q is the quotient and A is the remainder. So if we consider the decimal division, 136 divided by 9. So we'll get 1 as the remainder and 15 as the quotient. So we have got binary of 15 as the quotient and 1 is the remainder in binary. 0001 is 1 in decimal. So we have got the same value. So by doing this kind of manual division, you can verify your answer. Now let us also determine the sign of the final result, because that is very important. So here the sign of Q will be AS XOR BS. Basically, you have to find the XOR of the sign of the dividend and divisor. So we know that our divisor was negative and dividend was positive. So obviously the XOR of two signs, 0 XOR 1, will be a 1. And that's why this quotient will be negative. So this will be the sign, the final QS. And to determine the sign of the dividend, whatever is the sign of we need to decide the sign of the remainder, so that will be the sign of the dividend, the original sign of the dividend. So our dividend was plus 136, so remainder will be plus 1. So AS will be a 0 and QS will be a 1. So this will be the final sign of the result, and this is how this method is used to perform binary division.